The near-field area remains entirely multifocused, as we will discuss later regarding focusing, providing you with high resolution in the near-field area. Now here is your transducer, and here is the near field and the far field. The far field experiences divergence, while the near field experiences convergence regarding momentary interventions. You will find two things. The first is the divergence angle and the length of the near field. The length of the near field depends on the diameter of the transducer. If the diameter of the transducer increases, the length of the near field will also increase, if the frequency increases. The length of the near field is supposed to increase, meaning that if the frequency and diameter of the transducer increase, what happens? The divergence angle depends on two things: the wavelength, which is dependent on frequency, and the diameter. You will find that if the frequency increases or the diameter increases, your divergence angle decreases. Don't be surprised, because you are talking about the sign of the angle, not the angle itself. Now, let's see. I have a transducer with a diameter of 10 millimeters and a frequency of 2 megahertz. What did I do? I increased the frequency from 2 megahertz to 4 megahertz. What happened? Here is the near field area, and here is the divergence area, or the far field area. What happened to the near field? Did it increase or decrease? It increased, which is good, and the divergence decreased because you increased the frequency. So there is a relationship between divergence and frequency. The diameter has an inverse relationship, right? When I increased the frequency, what happened? The divergence angle decreased here. Okay, let's look at the second example. I will now compare these two, the 10 and the 5. All I did was reduce the diameter. What happened is that when the diameter decreased, the near field decreased and the divergence increased. So, if the diameter of the near field decreases, the length of the near field will decrease and the divergence will increase. All right, let's compare. Here is 5 millimeters and here is 5 millimeters, and this is a frequency from 4 to 2. So you have decreased the frequency. When you decrease the frequency, the near field decreases and the divergence increases. So what do we conclude from this? We conclude that I have the length of the near field, which depends on the frequency and the diameter. The relationship between them is that if you increase the diameter and increase the frequency, what happens to the near field? It increases. Now, regarding the relationship between the divergence angle, frequency, and diameter, if you increase the frequency, the divergence angle decreases. If you increase the diameter, the divergence angle decreases as well. All right, doctors, it's a clear point. So, the pulse, as I was talking about, has a certain peak that represents the highest intensity or the highest level present in it, which is related to the amplitude of the pulse. So, I give a pulse, and then I give another pulse. All right? The pulse period is the duration of a single pulse, while the pulse repetition period is the time between the end of the first pulse and the beginning of the second pulse. This means that the pulse repetition period is the rate at which the pulse is repeated, while the pulse period refers to the duration of one pulse. Of course, there are three terms or three definitions: average, which is special average intensity, and there is pulse average. Pulse average refers to the average intensity within the pulse itself, while peak is the highest amplitude or highest energy present, or the highest intensity within the pulse. However, when you talk about average or special average intensity, this refers to the average value between the two pulses or between the pulse you are working on. What do you mean by this definition? It's just a definition, like you already know what pulse repetition period means. and what temporal average intensity is, which is considered the average or lost average between the existing pulses, not just one pulse. There is also the average for a single pulse. This is the shape of the beam profile. If I take a cross-section inside the beam, the area in the middle represents the center, which indicates the highest peak intensity, the highest peak present. The surrounding zone represents the average or average intensity present. As we said, the pulses have a part that is high and a part where the intensity is low. When you take the average, it appears like this. The center for you is considered the area with the highest peak or highest intensity for your pulses. There is something called pulse repetition frequency. Now I am giving a pulse. Then I place behind the 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 pulse. What does your transducer or probe ultimately give you? It gives us an image, right? When you are using the transducer during the imaging process, do you find that the image, for example, when you place the probe on the patient's body, the images don't appear immediately? Do they disappear or take time to show up? I mean, while you are holding the probe and the frames are running, the images appear, right? Or am I wrong? The images appear fine. Okay. If I say that the image is working, it means that while I have the probe on the patient, there was a transmission in the pulse, and there was a reflection in the pulse that came back, and I received it and translated it into an image in a simple way. So this frame or image is essentially made up of lines. What does that mean? It means that inside the transducer itself, there is a crystal or the elements that I was talking about looking like this. Let's assume this is my field of view. All this element represents a line. I don't know what it is doing. The lens from the pulse sends it perfectly. This set of lenses ultimately represents the frame for me. The more lenses there are, the better it is for the frame, especially with additional lenses in various configurations and arrangements to enhance the overall quality and performance of the frame significantly. The increase in the number of lenses per frame is good for the resolution and clarity, which is crucial for optimal results. Now you have more elements present, and these more elements give you, for example, when you send a pulse here at this specific point, these pulses that exist, if I have devices here, and also devices here, should mean that these pulses, when I connect certain devices, are expected. Thinking improves and returns and receives if I have a large number of lines, or 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 a large number of lines. It's not that if there is a group present in front of the angle, or a group present in front of the angle, it won't be as large. Therefore, if there is any simple small group or something you can reflect on and start receiving the signal that reflected from it and imaging it well, the angle ratio, if increased, enhances the resolution with you, as I will discuss later in detail regarding image quality. But we want to say that if this angle increases, what does it mean? It means that the pulses that will be formed or that will occur from your transducer should also increase. Okay, in this case, if I say that pulse repetition frequency is the number of lines per frame, multiplying by the frame rate, what does this mean? For example, I am currently given an image frame. This frame contains a set of lines, say 120 lines, 200 lines, or whatever your number is. These lines represent a single image. Now, these lines actually represent the pulses coming from the transducer. If the frame time for one frame is, for example, 1 microsecond, and my transducer's efficiency allows it to produce, say, 100 frames per second, then 100 frames per second is the frame rate. The frame rate means the number of frames the transducer can produce in 1 second. So if I say the frame rate, I want to know how many frames or images I am producing per unit of time, meaning in a certain time period. This is what I call the frame rate. Now let's look at the presentation, such as this one. Of course, the number of lines per frame is 100 lines per frame. Now, if you need a high number of frames per second, then it is available. You need a high number of frames per second, so it is available. Why? Because if the number of frames is low, you will find that the image is flickering. The image does not appear to you as a continuous visualization or continuous displaying of the image. So you want the images that come out, or the frames that will be formed per second, to be many, so that you do not feel that there is a delay in the display of the existing image. So this story depends on what? It depends on the lines per frame. The more lines there are, the more time is given in the process of receiving the signal and translating it into the image. Now, if I want to take a definition of pulse repetition frequency, the pulse repetition frequency, so now I am sending my signal and receiving it. The process of repeating the pulses is the pulse repetition frequency. This depends on two things: the frame rate, which is how many frames per second you have, and the number of lines present per frame. If you have a frame rate of 30 frames per second and each frame has 100 lines, then multiplying the two will give you 3 kilohertz for the pulse repetition frequency. This means this is the rate at which the frames are repeated in 1 second. Now, if the pulse repetition frequency is high, then you are increasing the frequency of your pulses. So, at that time, the frequency will increase. The pulse repetition frequency is also related to the frequency of the ultrasound pulses present. Okay. Certainly, of course, each component needs a line. Not all components work at once, right? The waiting time should definitely be reduced significantly, and they absolutely must work one at a time. And indeed, they really should only operate individually. We will talk about it in the process of the probe itself. You will find that you want to do something called focusing, because focusing is done. So what does it do? It starts by working on taking a group of elements, for example, the first 4 or the first 5. It begins by firing the outermost or the outer ones first. Then it starts working on those in between. And after that, it leaves the first one and takes 4 from those it has already taken, and then it takes 1 from the new ones. I mean, let me show you a better picture. The firing process doesn't happen all at once. Look here, doctor, for example, what did he do? Here are 1, 2, 3, 4, 5. Take these, okay? What are these lines? They will be played for a specific line, all right? He is working on these, for example, and then he leaves this and takes the next group. Then he leaves that and takes the next group, and then he leaves one and takes the next group. This is because we will talk later about the topic of focusing, which is that you want to focus the beam in a specific way. All right, in order to enhance the focusing present in the beam, we need to understand that this focal zone is the area that has more homogeneity for the beam, the area that has higher resolution. So, he wants to capture images in this area. How will he achieve this focusing? This is what we will discuss next time, God willing, how beam focusing is done. All right, doctors. So, the pulse repetition frequency is basically the frame rate. This frame is the image. And within the image, there are lines. These lines are typically 100 lines per frame. Is that clear? 100 lines per frame, that's the product of the lines by the frame and the number of frames you will do per second, which I call pulse repetition frequency, to determine the location. As I mentioned before, I want to get the distance from which the signal came. Speed in time divided by 2 is given by this equation. Speed in time divided by 2 tells us where this comes from. I mentioned that when you send the signal, it takes time t to return. So that's 2t. When you get the distance, which is the velocity in time, this time you received is considered 2t, meaning it's not one way but two ways, which is going and coming back. So you divide by 2. This is what I express as the distance or the depth, which is the location from which the signal is coming to me. This is the equation for the pulse repetition frequency, which is also known as the pulse repetition frequency. What is the time if I say now that I consider, well, if I have a unit of frequency, the same idea applies if you have, for example, one pulse or one frame, then in this case, there is a relationship between it and time, or there is a relationship between it and the time of reception. To elaborate further, this relationship is crucial in understanding how frequency and time interact in various scientific and practical applications. So, if you want to know how to relate this topic, you can remove the t that exists in the equation we were saying. Equals in. This removal simplifies the equation, making it easier to comprehend and apply in real-world scenarios, especially in fields like physics and engineering, where precise calculations are essential. Understanding this concept can significantly enhance your ability to analyze and interpret data related to time and frequency. The velocity in t is equal to t, and we replace it with 1 over PRF, which is 0.5 times c, the velocity over pulse rate frequency, okay? In c over pulse rate frequency. What is the relationship between frequency and time? Well, frequency is the number of cycles per second, right? So if I have one cycle, then the frequency is 1 over time. The same idea applies to the frequency. Related to the repetition time, it's 1 over time, right? What were we calculating from this entire equation? We were calculating the depth or distance from which the signal came, right? Remove the t from the equation. What do we put 1 over? God bless you. It would be 1 over PRF, which is pulse repetition frequency. That's what it does, right? But he wants to link it to the machine parameters. The machine will distribute the pulse rate. That's the factor. Or the parameters you'll have in something called power and something called intensity power. He told you that the ultrasound pulse entering the patient is a form of energy transfer. The rate of energy transfer is the energy transfer rate, and its unit is watts. So, the rate of energy transfer per area unit, watts per square centimeter, is the intensity. Okay, so if we were to clarify, even in the context of radiation, we would say that power is the rate of transfer of energy, regardless of whether it is transferred. You have energy that is being transferred at a certain value. Now, if this energy is transferred over a certain area in a specific location, then I would call this intensity for you. Okay? Well, there is a need to express the intensity of the ultrasound pulse that is already incident. For example, if I have the probe like this, and this is the pulse that is coming down is the incident one. Let's go back again, but excuse me, the part about the power here. We assume that I have a transducer. I assume this is with me. The beam comes out like this. Here is the shape of the beam and the parameters I have. Here is the beam's output in a specific area. As you lower the beam, it experiences divergence and the area increases. So the intensity is the power per specific area, which is watts per square centimeter. The power is considered the energy that is transferred, the rate of energy transfer, and the power is essentially what is being transferred. But the area is specific in this specific area. The intensity is related to it, even the one I was just talking about. I have a transducer like this. This transducer has a frequency of 6 megahertz, for example. Is that clear? So, what about this? The pulse will be sent for you, and this pulse will move through the tissue. After that, it will go to Egypt, meaning it has moved from the tissue area, and then it will cross the border between the tissue and go to Egypt. While it is moving, there is an interaction between this pulse and the existing tissue. We will talk about these interactions, which involve loss of energy, leading to attenuation. The amount of attenuation that occurs is the amount that happens.